Mr. True. You guys are a trip. All right, Taylor polynomials and approximations. So we've been doing a lot of sections of determining if series converge or diverge, and we're going to put that on the shelf for just a tiny bit of time. We're going to be looking at polynomials that are used to estimate the values and actually the behavior of other functions. So if f has n derivatives at x equals c, then the polynomial p sub n of x, so the p stands for polynomial. The subscript is basically the degree of your polynomial. P sub n of x is equal to f of c plus f prime of c times x minus c to the first power over 1 factorial, which you will not see this in the textbook. I'm just writing this to build up the pattern of what's going on, plus the second derivative of f at c of times x minus c squared over 2 factorial, plus the third derivative of f at c times x minus c to the third over 3 factorial. And then this addition of terms just goes on until you get to your nth term, your last term. We have f of n of c times x minus c to the n power over n factorial. And that's called the nth Taylor polynomial for a function f of x, some other function f of x at x equals c. So soon we're going to go from a partial sum, a polynomial up to a Taylor polynomial up to a fixed degree, to where this addition just goes on forever. And instead of a Taylor polynomial and Maclaurin polynomials, there'll be Taylor series and Maclaurin series. And that is when you're going to see the purpose for all of those different types of convergence tests that we spent so much time on between 9.2 and 9.6. We'll be finding the endpoints of where the endpoints of convergence for the Taylor series and Maclaurin series. If it turns out that your center of convergence is just a specific number of c, that's going to be then called a Maclaurin polynomial. A Maclaurin polynomial is just a type of Taylor polynomial. A Maclaurin series will be just like a Taylor series, except the center of convergence for a Maclaurin polynomial and series is going to be equal to 0. So what we're going to do is we're creating polynomials that act like other functions. We're going to, for our first example, find the third degree Taylor polynomial for the function f of x is equal to the cosine of x centered about c is equal to pi over 3. Pi over 3 is going to be our center of convergence. That's what I'm going to be calling it when we talk about Taylor series. We are going to ultimately use this Taylor polynomial centered around c is equal to pi over 3 to use a polynomial to estimate the value of the cosine of x somewhere else. Like, we know what the cosine of pi over 3 is because we know the unit circle. To analyze and obtain a cosine value off of one of those 16 angles that are on the unit circle, we might have a few more that we can add in with the sum and difference and the half angle identities. But if we don't have one of those special cases and we need to estimate like maybe the cosine of 0.7, which that value is close to pi divided by 3, we might need, you know, some, like nowadays with technology, we can literally type anything into a computer and out comes an answer. But what's happening in that computer? What did they do before they had computers and everything was on, like, you know, iPhones and TI and Spires and whatever? There were slide rules and tables of values that people used as references to make approximations. And that's kind of what we're doing here. Ultimately, later on, you can also use Taylor polynomials to find derivatives and integrals that otherwise you wouldn't be able to, right? We basically at this point have what? About 17 or 18 derivative rules and maybe like 18 integration rules. There's a lot more than just 18 or 19 functions. So it might be we might need to take derivatives and integrals of functions that we otherwise cannot work with. But if we can make a polynomial, some degree polynomial, act like another function, polynomials are very easy to take derivatives and integrals of. So there's a lot of uses for this mathematics that we're starting to study, but we're just coming to the end of Calc 2. we're not going to really see those applications. We're just being exposed to the fundamental mathematics. Okay? So a lot of rambling of like why you want to learn this. So let's actually do the problem. And I'm going to draw what we're doing in this problem as we go along. So let's see here. We want to find a third degree Taylor polynomial, which means we're going to have to take a derivative for a third degree Taylor polynomial. Here where we have x minus c to the third, we need to find that third derivative. So we have f of x, of course, is going to be equal to our cosine of x. F prime of x, the derivative, what's the derivative of cosine? Negative sine of x. I'll pretend like I didn't hear the sign error. The second derivative of x, what's the derivative of negative sine? Negative cosine. There we go. And the third derivative of x, the derivative of cosine is negative sine, but this is negative cosine, and so you all, like just write the dang answer. It is sine of x. So, okay, so we're going to be coming up with a p sub 3 of x. So we needed f of c, and f prime of c, and a second derivative of f at c, and a third derivative of f at c. So now that we have this list of the function including up to its third derivative, our c, our center of convergence, is pi 3. So f of pi over 3 is the cosine of pi over 3. And I'm not going to write that for every single one of them. What's the cosine of pi over 3? 1/2. Then we have f prime of, yes I am, pi over 3. So that's going to be negative sine. I just said I wasn't going to write this, but we need it for notes. Negative sine of pi over 3. What's the sine of pi over 3? Square root of 3 over 2, and now it's negative. So negative square root of 3 over 2. F double prime of pi over 3, which is negative cosine of pi over 3, which is going to be negative 1/2 this time. And then we have f, the third derivative of f at pi over 3 is going to be the sine of pi over 3, which is, well, just square root of 3 over 2. So p sub 1 of x, which is not what the question's asking for, is going to be equal to, for the purpose of the notes, even though this question is asking for the third degree Taylor polynomial, we're going to graph what the cosine function looks like, and then I'm going to sketch. I've done it on my calculator, but since we're on the board, I'm just going to sketch what the first degree Taylor polynomial looks like, the second, and then finally the third. So you can see how these polynomials start to act more and more like our original given function around the center of convergence. So p sub 1 of x is going to be f of c. So it's going to be, let me write this, I'll write this out for notes. It's going to be f of pi over 3 plus f prime of pi over 3 times x minus pi over 3 over 1 to the first power. And so what was f of pi over 3? That was equal to 1/2. And then we're adding a second term, which is f prime of 3. Well, f prime of pi over 3, was equal to negative square root of 3 over 2. So we have a minus square root of 3 over 2 times x minus pi over 3, and 1 factorial is just going to be 1. So we have 1/2 minus square root of 3 over 2 times x minus pi over 3. So over here, let's draw out what this looks like. So let's see, we got pi over 2 and pi. But I think that might be, let me go to 3 pi over 2. And of course we have pi over 4, 2 pi over 4, 3 pi over 4, and pi over 3 is a little bit less than, or a little bit greater than pi over 4. So let's put that magic number about right here. So that pink dot is x is equal to pi over 3. What is the cosine of 0? 1. What's the cosine of pi over 2? 0. What's the cosine of pi? -1. Of course we know these answers. We're at the end of Calc 2, right? At the end of Calc BC. We have negative pi over 4 and negative pi over 2. And of course the cosine of negative pi over 2 is also going to be 0. So this is a graph of y is equal to cosine of x. If you see here in our problem, our center of convergence is pi over 3. And the first degree Taylor polynomial is what? It's a lot of stuff, but that's x to the first, so it's going to be a line. So our first degree Taylor polynomial is going to be tangent. It's going to be a tangent line. It's going to be tangent to the cosine function at the x value of pi over 3. So this is our first degree Taylor polynomial. So that's what our first degree Taylor polynomial is roughly going to look like. Now, if we find our second degree Taylor polynomial, p sub 2 of x is going to be f of c, so 1/2 minus f prime of c times x minus c to the first. So that's going to be, we already have that, minus square root of 3 over 2 times x minus pi over 3. But that's first degree. Now we need to bring in our second degree term. So we need the second derivative of f at c. So f double prime of pi over 3 came out to be -1/2. So we have -1/2 times, now we've got x minus c squared, so there'll be x minus pi over 3 squared. And our denominator is going to be a 2 factorial. We're not going to talk about this today, but in a video I already have posted on YouTube, I have a full expansion involving Taylor series, and you can see where this pattern comes from. So now what do we have here? 2 factorial is what? 2, right? And then 1/2 times 1/2, or 2 times 2 in the denominator, is going to be a 1/4. So our second degree Taylor polynomial is 1/2 minus square root of 3 over 2 times x minus 3 minus 1/4 times x minus pi over 3 squared. Now if you were to put that into your calculator, this is what kind of polynomial? It's a second degree or a parabola, and our x squared has what kind of leading coefficient? Negative. And so this is a parabola opening down. So we still have a center of convergence of pi over 3. That's the root, basically that we're using to create our polynomials with. And if I try my best to make a upside down parabola, it's going to look something, I'm also referencing, so we're going to go past 1. It's going to be something that looks like this. And I understand this is by hand, but we can see that the second degree Taylor polynomial is tracking the shape of the cosine function much broader in a much wider interval than just the linear function that just has that point of tangency. Now, if we come in and actually answer the question, which is to create a third degree Taylor polynomial, is going to be 1/2 minus the square root of 3 over 2 times x minus pi over 3 minus 1/4 times x minus pi over 3 squared. Okay, now we got to work in our third term here. The third derivative at c. So the third derivative of x, or basically sine of pi over 3, is a positive square root of 3 over 2. So plus square root of 3 over 2 times, I don't know why I'm using parentheses, times x minus pi over 3 cubed over 3 factorial. So what's 3 factorial? 3 times 2 is 6 times 2, and maybe I'll leave it this way. That's going to be 12. So it's square root of 3 over 12 times x minus pi over 3 cubed. Now, so you're putting, if you grab the graphing calculator, which I've already done, if y sub 1 is the cosine of x, if y sub 2 is this equation in red, if y sub 3 is the green one, and y sub 4 is the blue one, this is a what? X cubed. This is a cubic function. And the leading coefficient is positive. So your end behavior is, as x approaches negative infinity, the function approaches negative infinity, and likewise on the positive side are basically down to the left and up to the right. And just to draw this reasonably to scale, we have a third degree coming in. It looks like it probably comes in around here somewhere, and then tracks this cosine function pretty well. There is an interval between somewhere around maybe like, let's call it 1/6, 1/8 pi over 8, all the way out to almost pi, and even beyond a little bit. The cubic function falls below the cosine function in here. I have it above it, but it actually falls a little bit below. But it does a much better job, right? So the higher the degree of the polynomial, the more it tracks the function that it's derived from. And that is the purpose and the visualization, hopefully it's good enough, of what we're doing through the creation of these Taylor and Maclaurin polynomials. Example 1 done. Okay, so I said we were going to use these for approximations. Second example, I said you were going to be using these Taylor polynomials to estimate values and behaviors of other functions. Right now, just the value part. So we're going to use our third degree Taylor polynomial to estimate the cosine of 0.7. So, we've done all this work just because maybe we don't have some technology handy, or maybe we're learning, the inner workings of calculators. We're going to estimate the cosine of 0.7. Arguably not using a calculator, except I would not want to do this calculation by hand, to be honest. But at any rate, f of x will be approximately equal to the third p sub 3 of x. Or in other words, p sub 3, or f of 0.7 is going to be approximately equal to p sub 3 of 0.7. So what do we have here? We've got our polynomial over there is going to be 1/2 minus the square root of 3 over 2 times 0.7 minus pi over 3 minus 1/4 times 0.7 minus pi over 3 to the second power plus square root of 3 over 2 plus square root of 3 over 12 times x minus, no, not x, times 0.7 minus pi over 3 cubed. Now, just a second ago, you asked me an excellent question.
So why are we putting 0.7 in for x and not pi over 3? Like, what does pi over 3 mean?
You're an excellent actor. That was so overdone. Your pi over 3 is your point of tangency, basically, for the first degree Taylor polynomial, or the center of convergence, we're going to call it, for the Taylor series and Maclaurin series. These aren't full-blown series or polynomials. But the pi over 3 is like, that was the point on the cosine function that we used to create the polynomials with. And so the pi over 3 is a permanent number. That's your C. That's your center of convergence. We're not talking about convergence because these aren't series, but that's what I'm going to keep calling it. The value of, the x is your independent value. That's going to be the value of x that you're using, or where you're going to use the polynomial to estimate values of some original given function. So this looks really, really complex, and I definitely would not want to do all of this without the aid of a calculator, but it could be just like a 4-function calculator. Whereas, analyzing the cosine of 0.7, you need a scientific calculator. So it is, to a degree easier. And that is going to come out to be p sub 3 of 0.7 is going to be approximately equal to, okay, so how do we choose what your center of convergence is, or what C you're going to use to make your Taylor polynomial? You're going to be wanting to use any value basically of x, because this is a specific value of x. You're using a value of x. You're choosing this basically thinking about what is your original function and what can you evaluate your original function exactly at. Now this is just cosine of x, so I'm going to pick an angle that's off the unit circle, and I'm going to be using a C for which I can find an exact value for, in this case, cosine that is close to the value of x that I want to make an approximation at. So it's not totally random. That's a good question. How do you choose C? Oh, no, this is wrong. I copied the wrong answer. Try again. Cut, redo. Looked at the wrong number in my notes. I would have been better off letting you guys give me some help. So from our polynomial, p sub 3 of 0.7 is equal to 0.7645. And since we do all have calculators on our tables and desks, let's go ahead and figure out what is the cosine of 0.7. That's approximately equal to, maybe I'll write an equal, it's going to be rounded off, but I'm going to write equal sign indicating like it's more accurate. It came from a calculator. It was 0.76482. Okay, so since we have the luxury... 484?
Yes.
Okay. Or maybe this is 4 decimals. Let's just go ahead and stop there. So since we have the luxury of actually finding the value that we're trying to estimate, let's go ahead and calculate the error. What is the difference between the predicted value from the third degree polynomial and the quote-unquote actual value, even though we know it's rounded off to a degree? Your error is going to be equal to 0.7648 minus 0.7645 for an error of 0.0003. So tenths, hundredths, thousandths. We are off by 3 10,000ths of a unit by just using a third degree Taylor polynomial to estimate the value of a cosine function. And you do again have to be relatively close to that center of convergence, but that is remarkably close, which is really cool. So that begs the question, what did we talk about in an alternating series? We had an alternating series error, a remainder. So if you go to estimate an unknown value, if you make an estimation, you really need to know what is the maximum value that error is off. We do have an error. How big could it have possibly been? So what is the maximum error from an approximation when you use a Taylor polynomial? Guess what? That's next. Pause. Gotta write this. So we got an estimation of cosine of 0.7 from our third degree Taylor polynomial to be 0.7645, and we could actually estimate or calculate that actual error since we could just type the cosine of 0.7 in our calculator. But if that were not possible, what would be the upper bound? What's the largest possible error for that approximation of p sub 3 of 0.7 for the cosine of 0.7? So that is going to be, enter the Lagrange form of the remainder. So f of x is going to be equal to some, p sub n of x. I'm going to just be saying, I'm just going to assume this is a Taylor polynomial, though it could be a Maclaurin. But f of x is equal to p sub n of x plus r sub n of x, a remainder. You're going to get an estimation from your Taylor polynomial, and then plus that, you're going to add some kind of remainder. Now, I'm writing equal, but we're just going to find an upper bound of that remainder. So arguably, maybe that should be an approximation. But so p sub 3 of x then becomes, then we get from that equals p sub 3 of x plus r sub 3 of x. Well, our third degree Taylor polynomial, which estimating cosine of x about the point pi over 3, or c is equal to pi over 3, we got that 1/2 minus square root of 3 over 2 times x minus 3 minus 1/4 times x minus 3 squared plus square root of 3 over 12 times x minus pi over 3 cubed. Now, to that, we're going to add r sub 3 of x. What is that remainder? R sub n of x, the Lagrange form of the remainder, is going to be equal to the n plus 1 derivative of f of z times x minus c times n plus raised to the n plus 1 power over n plus 1 factorial. And of course, I erased the board so I can continue writing notes, and I've taken arguably too much off. What was our original function again? F of x was, of course, cosine of x. F prime of x was negative sine of x. The second derivative of f of x was then negative cosine of x. The third derivative of f of x was derivative of negative cosine, sine of x. And then our fourth derivative of x is going to be cosine of x. So this formula for the Lagrange form of remainder, does it strike any kind of familiarity, any kind of similarity between this and the alternating series error? They're both what? They look kind of familiar. What was the remainder for an alternating series? The remainder, the error, when you estimated the series value from a partial sum, your maximum possible error was basically less than or equal to a sub n plus 1, your first neglected term. So we just made a third degree Taylor polynomial to estimate the cosine of x around the c of pi over 3. And the r sub 3, the remainder, the Lagrange error, is r sub n is the what? The n plus 1 derivative. And the x minus c is to the power of n plus 1. So arguably, this is yet again, it's called something different, and it looks a little bit different in form, the Lagrange form of the remainder versus the alternating series error. But this next term is what? It's really the first neglected term. We need to write out an expression for r sub 3 of x. So from here, we have r sub 3 of x is going to be the fourth derivative of f, and the fourth derivative of f of x is the cosine of x. So we're going to have the cosine of z, not pi over 3, times x minus pi over 3 to the n plus 1 or fourth power over n plus 1 or 4 factorial. Now, we're going to bring that answer down in here for a second. What is this z that is in the Lagrange form of the remainder? So we have a similarity to the alternating series upper bound, which is we're working with that first neglected term, but there is some additional complexity. C is our center of convergence, or the point at which we started creating our Taylor or Maclaurin polynomials. X is, where you are making your approximation at. So for our problem, x is 0.7. We want to find the upper bound, the largest possible error on some closed interval, and that's where the z comes in. Z is somewhere on the closed interval between the center of convergence or the center of your Taylor polynomial and where you're making the approximation at. And so this is a closed interval. We have the closed interval from c to x or from x to c. This is just because I don't know if you're making an approximation to the left of the center or to the right of the center. So, but somewhere on this closed interval, z is basically a value of x that's going to make your n plus 1 derivative as big as possible. You want to make, it's okay if you're more accurate than stated, but not okay if you're less accurate than stated. So we want to maximize that area. Now, we have a bit of a special case here because we're using just sine or cosine for this example. So for most questions, you're going to have to find that fourth derivative, or the n plus 1 derivative, and you're going to have to analyze it on the closed interval. And you may be using a value of x that is c, a value of x that is x itself, or the value of x, or I'm saying x, but z is a form of x. It is a specific value of your independent value variable. Or it might be somewhere in the closed interval. But for our early textbook questions, z is probably going to be one of the endpoints, but it could be somewhere in the middle. But we are wanting to find the maximum error. And for convenience, we're going to just say this. For most questions, you'll be checking for a maximized error, which means you're maximizing, again, that n plus 1 derivative on the closed interval from c to x or x to z. But since in this case, our n plus 1 derivative is either going to be positive or negative sine or positive negative cosine, in absolute terms, what's the largest value you can get from sine or cosine? 1. So since we're just trying to find the maximum possible error and do this as efficiently as possible, we're just going to let that maximum value that the n plus 1 derivative can take on, we're just going to default to 1. So we don't actually have to analyze what the biggest value cosine will give somewhere between pi over 3 and 0.7. We're just going to set the maximum error, the maximum value of the n plus 1 derivative to 1, just to be convenient. And you'll be able to do that anytime you are making a Taylor polynomial for either sine of x or cosine of x, and regardless of what the center of that polynomial is. So r sub 3 of x is going to be, and our x is 0.7, is going to be 1 times 0.7 minus pi over 3 to the 4th power over 4 factorial, which is 4 times 3, which is 12, times 2, which is 24. And that is going to come out to be, in this particular case, bum, 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 0.0061. And so we created a Taylor polynomial for the cosine of x centered around pi over 3. We used it to make an approximation at the value of 0.7. We found, that p sub 3 of 0.7 was a value. This is the largest that estimation can possibly be of. And that is the Lagrange form of the remainder. Rest assured that in your free responses, question number 6 is always from chapter 9, or at least it always has been in the past. You have a very, very good chance in question 6 to be asked to, calculate a maximum possible error for a alternating series or for a Taylor polynomial. So this is most likely going to be a part of one of your free response questions. Does this make sense? So let's just continue this problem even farther. So we have that function that we created. We have we want to estimate the cosine of 0.7 using the center of a polynomial. C is equal to pi over 3. So we still have that polynomial over here. P sub 3 is equal to the polynomial we came up with, that third degree Taylor polynomial. But now we don't have that third degree Taylor polynomial. I just want to estimate the cosine of 0.7 using a center of convergence or a center for the polynomial to be pi over 3, what degree Taylor polynomial would we need? Determine the degree of the Taylor polynomial or Maclaurin polynomial required for the error in the approximation for the cosine of 0.7 at using the center of pi over 3. I want that error, that maximum error, to be less than 0.0001. So we used the third degree Taylor polynomial and got a maximum possible error of 0.00061. I would need to reduce it down to 0.0001. Tell me the degree of that polynomial. Okay, so we have some predictions. What are we going to use? What tells us the remainder of a Taylor polynomial? The Lagrange form of the remainder. So this form of the remainder, this Lagrange form of the remainder, needs to be what? Less than or equal to 0.0001. So what is the n plus 1 derivative of f of z going to be? What's the maximum sine and cosine ever equal? 1. So we have 1 times, what's our x? 0.7 minus our c, which is pi over 3 to the n plus 1 power over n plus 1 factorial. That needs to be less than or equal to 0.001. Oh, missed a 0. Another 0.1. How are we solving that? This isn't an equation you can solve.
Yeah, guys.
So what are you going to do?
Make n by
No. You're just going to use technology to do trial and error. So you can type this expression in for y sub 1 and then create a table of values starting at 1 and count by 1, or just hope that n is relatively small and just start plugging in small numbers. And by the way, I'll give you a hint. It's just the next one. So trial and error will tell you that it's going to be equal to 4.
it wasn't 6 or 7.
Yeah, we were guessing some much bigger numbers. So with trial and error with our calculator, we're going to get n needs to be 4. So just a 4th degree Taylor polynomial centered around pi over 3 will get you an estimate that is almost exact. I have a feeling that's actually what's happening with calculators when we just type stuff in to the calculator and ask it to do some work. So I'm going to give you one on your own to try. I'm going to give you an example to try on your own. Let me edit this into our lesson. I realized that I forgot a line of notes in my lesson today that, yes, the Lagrange form of the remainder, that r sub n of x is equal to the n plus 1 derivative of f of z times x minus c to the n plus 1 over n plus 1 factorial. But when you are calculating the error, but the difference between the actual function value and the estimated value found by the nth degree Taylor polynomial, the error is the absolute value of r sub n of x. So as I did my examples, when my second example had a remainder that was coming out to be negative, I realized that absolute value needed to be there. So I'm just adding it to my notes and your notes. So let's give this one more walkthrough to make sure you completely got it. We are going to approximate f of 2.2, where f of x is equal to the natural log of x, using a 3rd degree Taylor polynomial centered around c sub 2. So the first thing we're going to have to do is come up with that 3rd degree Taylor polynomial, which means centered around 2. So that means p sub 3 of x is going to be equal to f of 2 plus f prime of 2 times x minus 2 to the first, and if just for notes, even though we know the answer is 1, over 1 factorial, plus f double prime of 2 times x minus 2 to the 2nd power over 2 factorial plus f, the third derivative of f at 3 times x, at 2 times x minus 2 to the third power over 3 factorial. We're going to find that polynomial, then we're going to plug in 2.2 and get our approximation. And then we're going to find the upper bound of that approximation. So we need to find and work with f of x, f prime of x, f double prime of x, and the third derivative of f of x. So f of x is that natural log of x. The derivative of natural log of x, of course, is going to be 1 over x. Derivative of 1 over x, that's really x to the negative 1. So we're going to bring that power down and then reduce the power by 1. So we have negative 1 over x squared. And then the third derivative, even though I'm writing this as negative 1 over x squared, for derivative's sake, I like to think of that as negative 1 times x to the negative 2. Bring that negative 2 down, so negative 2 times negative 1 is 2, and reduce the power by 1, and so we have 2 over x cubed. And that's going to be all we need for finding that third degree Taylor polynomial. But the second part of this question is, what's the upper bound of your approximation? And for that, we know from the Lagrange form of the error, we need the first neglected term, or that fourth derivative. So the fourth derivative of x, thinking of this as 2 times x to the negative 3, is going to be negative 6. 2 times negative 3. Reduce that power by 1, so we have negative 6 over x to the fourth. So now we need to find f of 2, f prime of 2, f double prime of 2, and f third derivative of f at 2. So we're just going to take this list of derivatives and plug the value of 2 in them. F of 2 is the natural log of 2. F prime of 2 is going to be our 1/2. F double prime of 2 is going to be negative 1 over 2 squared, which is 4. The third derivative of f at 2 is going to be positive 2 over 2 cubed. But of course, 2 to the first over 2 cubed is going to be 1 over 2 squared, which is once again going to be 1/4, only this time for the third derivative positive as opposed to being negative for the second derivative. And that makes our third degree Taylor polynomial equal to p sub 3 of x is going to be the natural log of 2 and then plus 1/2 times x minus 2 to the first. Our next term is going to be determined, start with the second derivative of f at 2, which was our negative 1/4, so minus 1/4 times x minus 2 to the second power over 2 factorial, which I'm going to simplify this to be negative 1/8, right? Because 2 factorial is 2. So minus 1/8 times x minus 2 squared. And then our third derivative at 2 is equal to 1/4, so plus 1/4 times x minus 2 cubed over 3 factorial, which 3 times 2 is 6, times 4 is 24. So plus 1/24, or 1 over 24, times x minus 2 squared. Just making sure I don't make a small mistake. So this is our third degree Taylor polynomial that's going to act like, be used to estimate values and behaviors of the natural log of x around the center of our Taylor polynomial, which is equal to 2. So we're going to use this polynomial to estimate f of 2.2. So f of 2.2 is going to be approximately equal to p sub 3 of 2.2, which means we're just going to plug 2.2 into this equation and have the natural log of 2 plus 1/2 times 2.2 minus 2 to the first minus 1/8 times 2.2 minus 2 squared plus 1 over 24 times 2.2 minus 2 squared. And putting that into our calculator, we get f of 2.2, and hopefully I had this in my calculator correctly, comes out to approximately 0.78848. Now, you heard my class, they corrected me on the previous estimation. I missed a 0, but I'm pretty sure that this is our correct approximation. So the natural log of 2.2 using our third degree Taylor polynomial centered around x equals 2 or c equals 2 is approximately equal to 0.78848. Now, what is the upper bound? What is the largest? This is just an approximation. It's not exactly what the natural log of 2.2 is. So what's the largest this estimation can possibly be off? What's the upper bound of our estimate? What is the Lagrange form of the remainder? So our remainder based on our third degree Taylor polynomial is going to be the fourth derivative at some value of z that, again, maximizes, z is going to be on the interval between our center of 2 and the x we're making the approximation. In this case, x is larger than our center of the Taylor polynomial at 2.2. We need to figure out a z that is on this interval that maximizes our fourth derivative. So we'll be looking at that. Times, get the right marker out here, times x minus 2 to the fourth power over 4 factorial. But of course, the x, the location of our estimation, is not unknown. It's 2.2. And so this x is going to be 2.2. And we're going to take, I think I might have forgotten the absolute value of this later, early on. I might have. Yes, our maximum error needs to be the remainder of this. So I'll need to add that to my video notes. Okay, so so let's talk about the z that is going to make our fourth derivative function give a largest value possible. And again, remembering that I did forget on the Lagrange form of the remainder those absolute value symbols around that expression. So z is on the closed interval from 2 to 2.2, or somewhere in the middle. Usually in our early textbook problems, it's going to be one of these endpoints. But the fourth derivative, if that fourth derivative has a maximum value or minimum value somewhere on that closed interval, you may, on some really prickly problems, need to be able to figure that out. So let's take a look at this. Our fourth derivative is, I'll put this on the side and erase it in a minute, but our fourth derivative of x is -6 over x to the fourth power. Now, if you think about what some of our parent functions look like way back in pre-calculus, you might have had your very basic reciprocal function, like y is equal to 1 over x. That function, basically looked like this. You had a vertical asymptote of x equals 0 and a horizontal asymptote of y equals 0. Well then, if we take that function, y is equal to 1 over x, and think about what does y equal 1 over x to the second power look like? Well, when you plug in, I don't know why I'm writing this crooked, but when you take your negative values of x and put them in the denominator and square them, any number squared becomes positive. So the graph of y is equal to 1 over x squared, all on this left-hand branch of our reciprocal function where it's below the x-axis, all of those negative values of x are going to be squared before being placed into this denominator. So this equation is not going to yield any negative answers. So this is the graph, roughly a sketch of y is equal to 1 over x squared. Well, of course, this denominator has a power of 4, but that's another even power. So if you look at what y is equal to 1 over x to the fourth looks like, any value of x positive or negative being raised to a fourth power is going to become positive. So the graph of y is equal to 1 over x to the fourth is going to look, something like, something like this, where it's going to go approach 0 even faster. But it is going to be above the x-axis, both to the left and right of the y-axis. Now come along here, and you've got the graph of y is equal to 1 over x to the fourth having a transformation of -6 being applied to it. Well, the multiple of 6 is going to vertically stretch that graph away from the x-axis, but more importantly, that negative leading coefficient is going to reflect the graph over the x-axis. So this is the graph, at least a sketch, of the graph of y is equal to, or f of x is equal to -6 over x to the fourth. It's below the x-axis, both to the left and right of, it's going to be below the x-axis to the left and the right of the y-axis. Okay, so we want, again, that fourth derivative to yield the largest possible answer in absolute value. So if you have a graph that's increasing, maybe this is your x value of 2, and this is your x value of 2.2. That's getting closer to the x-axis as x increases to infinity. So right away I know that the fourth derivative of f at 2 is going to be a smaller number, but in absolute value it's going to be a larger number. But just to double check that, and there's not going to be any critical values between on the enclosed interval or between 2 and 2.2. So let's just figure that out. So we have the fourth derivative of f at 2 is going to be -6 over 2 to the fourth, which is going to be equal to -0.375. And the fourth derivative of f at 2.2 is going to be -6 over 2.2 to the fourth power. And that is going to be approximately equal to -0.256. And in absolute value, this is a smaller number, but when you take the absolute value, of course, it's going to make it positive, and you want to use that 0, so you want to use that negative 0.375, and we get that the r sub 3 of 2.2 will be equal to the absolute value of -0.375 times 2.2 minus 2 raised to the fourth over 4 factorial, which is approximately equal to, there's already probably some round off error here, but it's approximately equal to 0.0000, so we're getting really, really small numbers, 25. So that is the largest maximum error, which is pretty small, for our approximation of f of 2.2, which was 0.78848. That is my last example. Bam! Go do your homework.